Okay, hello and welcome back to another one of these A-level maths videos. So again, we're ploughing on with statistics as we've done for the last few weeks. But today, before we get on to the real meat of A-level statistics, which is the binomial distribution and hypothesis testing, we have to go through what probability is first. So this is literally the penultimate one right before we get to the binomial distribution and hypothesis testing, which is really the kind of interesting parts. So probability stays somewhat similar to GCSE, however there are some kind of new terminology and new kind of methods that we have to use. So first of all, we have Venn diagrams, again, same as usual, and we have a few missing pieces, P, Q and R, and part A just says write down two of the events that are mutually exclusive. So what does mutually exclusive mean? Well, it means that they both cannot happen. Okay, so both cannot be true. Okay, so both events can't happen simultaneously. Okay, so for example, when you flip a coin, right, you can get heads or you can get tails, but you can't get heads and tails, right? So you can only get one or the other. So that is what they mean by it. So in this case, what would that mean on a Venn diagram? Well, it means that there'd be no overlap. So the only two events that don't have an overlap are A and C. So for part A, the answer is just A and C. Part B, it says events A and B are independent. The probability of C is 0.3, and therefore we should be able to work out absolutely all of the unknowns. So when we say something's independent, it means that probability of A times probability of B should equal the probability of A and B. Okay. But in terms of what it means in kind of plain English, it just means that the probability of one thing happening doesn't affect the probability of another thing happening. So let's give some examples. So two events that are kind of independent is, let's say I flip a coin and also roll a dice. Those events are independent because it doesn't matter if I get heads or tails on the coin, it won't affect what I get on the dice. Now events that might be not independent are things like the probability I take an umbrella with me to work, right? That's dependent on whether or not it's going to rain, so the probability of rain. So that's kind of the two main examples that you can give. So how's this going to work for this question? Well, we need to find P, Q and R, and what we're going to do is use the fact that probability of A times the probability of B is equal to probability of A and B. So if we read that off, the probability of A is both of these probabilities added together. So 0.25 plus 0.15, which is 0.4. So 0.4 times the probability of B equals the probability of A and B, which is 0.15. Again, just looking at the Venn diagram, which means the probability of B is just 0.15 over 0.4. And then again, we can just use a calculator to quickly work out what that would be. So 0.15 divided by 0.4 gives me a value of 3 over 8, or 0.375. Now this is the probability that B happens. So what that looks like on the Venn diagram is it's all of these probabilities added together, right? This is the probability that B happens at all. Okay? So that is equal to 0.15 plus 0.1 plus P. So in other words, P is just going to equal 0.375, and we're going to subtract the other two parts, so 0.15 and 0.1, and that gives me the value of 0.125. Okay, so we've got P. That's pretty good. Okay, so I'm just going to mark that off as a tick. Now using that, it tells me the probability of C is 0.3, which means Q plus P equals 0.3. So Q is just equal to 0.3 minus 0.125. So therefore Q is just equal to 0.275. Or, sorry, 0.175. Basic maths is hard. Okay. Okay. And that gives us that. And so what about R? Well, R is the probability that none of these events happen. So if I add up all of these individual probabilities and take it away from one, that will be what R is. Because again, R is the probability that nothing happens. So R is equal to 1 minus 0.25 minus 0.15 minus 0.1 minus 0.125 minus 0.175. That is equal to, well, okay, I can't do that in my head. Well, I can, but I don't want to. 0.25 minus 0.15 minus 0.1 minus 0.125 minus 0.175. 1/5, which is obviously 0.2. Well done. Perfect. Okay, so with the Venn diagrams, they can get a little bit tricky, a little bit new at least. So, but on the right side, they are pretty much the same every single question. Okay, but that's kind of the method that you use here. Again, it's a 5-mark question, but again, each part isn't too tricky in terms of where you get the marks. You get a mark for stating this because they're independent, as it says here. You get a mark for working out the probability of B, a mark for working out P, Q, and R. Okay, so fairly easy to count the marks in these questions. Next question, again, it's another Venn diagram, but it does look different. Does look a bit different. So we have 2 that overlap and 1 that's just off by itself. So write down 2 of the events that are mutually exclusive. So again, the word mutually exclusive, or the term mutually exclusive, it just means that they both cannot happen at the same time. So the example I used was if I flip a coin, I can get heads or tails, but I can't have both. I can't have the probability of I can't get heads and tails at the same time, right? So in this case, heads and tails would be mutually exclusive events. So what that looks like on the Venn diagram, so just for the people that have just joined the live stream, is there will be no overlap between them. Okay, so in this case, it could be B and C or A and C. Because again, there's no overlap. And you only need to pick one pair. Okay. For part B, again, we have a similar question to the initial part here, but we have to find out what these missing values are. So probability of A is 0.4. So A being 0.4 means that every number inside this circle should add up to 0.4. So P is just going to equal 0.4 minus 0.2, which is, well, actually I'll write it down here, 0.2. Okay? Now, for the value of Q, so it tells us that they're mutually exclusive. We can also work out what R is later on, but the probability of A or B is 0.7. So what that means is every value inside both of these circles added up should add up to 0.7. So in this case, Q is going to equal 0.7 minus P and minus A, which is 0.2. Which is 0.3. And lastly, it says find the value of R. So the only way we can do that is add up all the other probabilities and subtract them from 1. So we have 1 minus 0.2 minus 0. There was another 0.2 for P, minus Q, which is 0.3, minus 0.1. And that's equal to R. So this is 2, 4, 7, 8, so that should be 0.2. Because 1 minus 0.8. Okay, so far hopefully this isn't too tricky, it's not too bad so far, it's a bit of problem solving. Now here you have to actually draw your own, part C, giving a reason whether or not the events A and B are statistically independent. So the way we do that is using this criteria here. So if you multiply them together, we should get the probability of A and B. So in this case, it's A and B. So I'm going to write C up here. Actually. So what we're going to do is work out the probability of A multiplied by the probability of B, which is 0.4 times 0.5. Which equals 0.2. So that should equal, if they are independent, it should equal the probability of A and B, which is the overlap between them. So in this case, it does equal B because P was equal to 0.2. So it does equal to probability of A and B, so independent. Hopefully that's nice and easy. So now we have to actually draw our own Venn diagrams, and to be honest, it's not the most tricky thing to do, but people do tend to make mistakes with them. So what we're going to do is, there are 3 sports: football, golf and hockey. So I'm just going to write out or draw out 3 circles. Actually, just make them a bit bigger to make them a bit nicer looking. I'm going to call them football, golf and hockey. And then what we like to do, what we have to do really, is we start from the middle and we work our way out. So what I mean by that is we're going to start with all 3 sports being liked. So here that would be 5 people, so we put 5 right in the middle. And then what I like to do is tick off as I go along. Now 8 people watch football and golf. So in this region here, there should be 8 people. Now we already have 5, so in the leftover should be 8 minus 5, which is 3. Tick it off. 7 people watch golf and hockey, so we're going to do the exact same thing. Here, in this region here, there should be 7 people. Currently there's 5, so we need to add 2 more. And lastly, football and hockey, there's 9, so we should just put 4 in here. So can you see we're starting from the middle, working our way out. Now it says 31 people watch football. So in this whole circle, there should be 31 people. So you have to include the overlap ones. So that's minus 3, minus 5, minus 4, because that's all these values that are already taken. Gives me 19. And again, tick it off. 13 people watch golf, so 3, 8, that'd be 10, so there should be 3 people in the golf section. And lastly, tick it off, 17 watch hockey, so 4 plus 5 is 9, that's 11, so there should be 6 people in the hockey only part. Okay, and then what people do is, okay, maybe they'll draw the box, but you do need to draw the box, and they'll leave it as that. This would be the wrong answer. You would drop a mark. Why? Because we need to verify if all of these numbers add up to 50. If they don't, the leftover needs to go outside the box. Outside the circles. So what we're going to do is literally do 5 plus 3 plus 4 plus 2 plus 6 plus 19 plus 3. That gives me 42, which means 8 people, because again 50 minus 42 is 8. 8 people should be outside all the circles. So a lot of people drop that mark. They also drop another mark when they don't draw the box. There has to be a box in a Venn diagram. Okay? Okay. So going with the Venn diagram, you get 3 marks by default. You drop a mark for every number you get incorrect or you don't put. So if any of these numbers are incorrect, you drop a mark, and you also lose a mark if you don't put the box. So basically, you have 3 mistakes, 3 chances that you have. B, it says 2 people are selected at random. Find the probability that they both watch football. Okay, so how many people watch football in total? It's 19 plus 3, so 22, 27, 31. So I'm going to write 31. Out of how many people in total? Well, it says at the beginning there's 50 people. So 31 over 50. And then another person that watches it? Well, it has to be a different person, right? You can't select the same person twice. So you have to subtract 1 from the top number and 1 from the overall. So 31 over 50. And that gives you how many? Actually, we'll leave it as a fraction just to make it a bit easier. 93 over 245. Like that. Okay. So, for the events A and B, the probability of A is 0.6, probability of B is 0.5, probability of neither A or B is 0.1. Okay. and it says find the probability of A and B. Well, if it's neither A or B, right, then 1 minus that is 0.9, and it will give you the probability of A and B. Okay? So now all you have to do is so again, there's two ways to look at it. You can either just do 1 minus that, or if you add these probabilities together and then subtract 0.9, that will give you what you're looking for. Because remember, this is neither A or B, so this is everything outside the Venn diagram. And we have both things inside the Venn diagram, but we want the overlap in particular. So the probability of A and B is just going to be 0.6 plus 0.5 and then minus the 0.9, which would give you 0.2. That's for A. For B, we're just drawing a Venn diagram for this information. So again, all we need is 2 circles, one for A and one for B. And once you see this, it should hopefully make a bit more sense as what the original is. If you're unsure, you can always draw the Venn diagram first. So A and B is the bit in the middle, so 0.2. Now, if the probability of A is 0.6, then everything inside this circle should be 0.6, but we already have 0.2, so it's 0.4. And using the same logic, this would be 0.3. Okay. So again, this neither A or B has to be outside both circles 0.1, which is why we did this calculation here. And then lastly, for part C, it says determine whether A and B are independent. So, if you want to work out if they're independent, you do the probability of A multiplied by the probability of B, which is 0.6 times 0.5, which is 0.3. Now 0.3 does not equal the probability of A and B, which is 0.2. Therefore, they are not independent. So in some way or another, they do depend on each other. So the probability of one, so if one event happens, it affects the probability of the other event happening. Okay, so again, if it's raining outside, it will affect the probability that I'll bring an umbrella or a coat with me. Okay. So two events A and B are independent, and the probability of A is 0.4 and the probability of B is 0.3. So we need to find probability of A and B. So because they're independent, the probability of A times the probability of B will give me the probability of A and B. Which means the probability of A and B is equal to probability of A 0.4 times 0.3. 4 times 3 is 12, so it would be 0.12. And lastly, for part B, you just need to draw a Venn diagram. Again, it's nice and, I want to say gentle, but that sounds a bit strange. Again, we know there's going to be an overlap because we have probability of A and B. So probability of A happening, so we want the overlap first. Let's put the 0.12 there. I never leave enough gap. And probability of A happening is 0.4. So 0.4 minus 0.12 is 0.28. And 0.3 minus 0.12 is 0.18. Now, where a few students would go wrong with this is they would not write something outside. So what we want to do here is we do 1 minus 0.28, 0.12, and 0.18. And we have to put this decimal on the outside because, again, all probabilities should add up to 1. Inside a Venn diagram is every possible outcome for a thing, right? Which means every single probability inside this should add up to 1, no more, no less. So if you're ever unsure, add up your values. If it doesn't add up to 1, there's a mistake somewhere, or you've forgotten to put the thing outside the 2 circles. But just be really, really conscious of that. Okay. I think everyone's okay with that? Perfect. Two events A and B are mutually exclusive. So what does that mean? It means that there'll be no overlap in a Venn diagram, and PA is equal to 0.4, PB is 0.3. So write down the probability of A and B happening. Okay, So how do we work this out? Well, we multiply them, right? No. Mutually exclusive means it is literally impossible for both things to happen. Okay? So A and B cannot both happen. Which means the probability of A and B is 0. The other way you can think of it is the A and B part of the Venn diagram is the overlap between A and B. If they're mutually exclusive, they shouldn't overlap, which means the probability should be 0. So again, what we're going to draw here is two completely separate circles. Don't even make them touch. Probability of A is just going to be 0.4. Probability of B is 0.3. And again, if you add those together, you get 0.7, which is not 1. So the bit on the outside needs to be 0.3. Be really careful and conscious of that. Okay, for the next part, all you're doing is drawing the Venn diagram. So, again, I do draw them a bit like potatoes just so I can make sure I can get the... actually fit the number in there. So probability of A is 0.6, so 0.6 minus 0.4 is 0.2, 0.5 minus 0.4 is 0.1. 0.2 plus 0.4 is 0.6, plus 0.1 is 0.7, so outside should be 0.3, 1 minus 0.7. Okay, so a box contains 10 milk chocolates and 8 dark chocolates. Connor takes 2 chocolates at random, find the probability he takes 2 dark chocolates. So what you want to do is look for the number of dark chocolates at the moment. There's 8. Out of how many? Well, 8 plus 10 is 18. And multiply it by, well, 1 dark chocolate's been taken, so now there's going to be 7 dark chocolates left, which means the total number is also gone down by 1. And let's work this out. So we have 8 over 18 multiplied by 7 over 17 gives you 28 over 153. So that's fine, but the second one is slightly more tricky. So 1 milk chocolate and 1 dark chocolate. So getting one of each, you can do that in 2 ways. You can have the probability that you get a milk then a dark, or you can have the probability that you get a dark chocolate then a milk chocolate, right? So since there's 2 possibilities, you have to add them together. So remember I said or, he can either do this or this. And what that means is you add those together. But you have to count all combinations, right? So if this was, he takes 3 chocolates, what's the probability he gets 1 milk chocolate? Then it's milk, dark, 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 milk, dark, 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 milk, right? So there'd be 3 outcomes. 3 outcomes that lead to the same kind of end result. So milk chocolate, then a dark chocolate, you will have, so milk first, you would have 10 over 18, multiplied by 8 dark chocolates remain, and 17 overall chocolates. Dark, so that'd be 8 over 18 still, and this would be 10 over 17. You want to add those together. Okay, so whoops, times 8 over 17. And you get 80 over 153. So just over 50%. That would be it. But again, it's very easy to make mistakes on this because you don't take into account all the combinations or something like that. Okay. Likewise, we have a bag containing 10 blue counters, 8 red and 6 green counters. 2 counters are to be removed from the bag at random. Find the probability that the 2 counters removed are both red. Well, that's fairly okay. So probability of getting 1 red, so there's 8 reds. Out of 10 plus 8 is 18. Plus another 6 would be 24. Multiplied by, well, there's 1 fewer red counters and 1 fewer counters overall. Whoops. (7/69). Now part B is where it gets ever so slightly interesting. So we need to find the probability that they're just different colours. So now we need to write down all of the combinations where you have blue and then red, red and then blue. You also have blue and green, green and blue, and lastly you have red and green, green and red. So that should be all of the combinations that you can get. Okay, let me just double check that. So you can get blue red, red blue, blue green, green blue, red green, green red. Yeah, and that's every single one. So one way to work out like the number of combinations you can have is if you take the number of possibilities, right, and you want to take it as a factorial. So what you're basically doing is you have 3 things you're combining factorial, which is the same as doing 3 times 2 times 1. So there's 6 combinations. We have 6 combinations here. Okay. If there was 4 different counters, then you'd have 4 times 3 times 2 times 1, right? And then so on and so forth. If you only had 2 things like in the beginning, you have 2 times 1, which is why we only had 2 combinations. Anyways, let's do it. So to get a blue-red, let's probably add that one first. Blue-red would be 10/24 times 8/23 plus red-blue. This is going to be extremely tedious. 8/24 times 10/23 plus blue-green. Again, some of these are going to be exactly the same, right? Which is completely fine. I know, the concentration on my face must be incredible right now. Because it's easy to make mistakes, especially when you're a bit tired after work. Well, I could do this on my calculator that I have in my hand, which might be easier, because then I won't, you know, it won't take as long. So give me 2 seconds, I'll just type it in. So 10/24 times 8/23 plus 8/24 times 10/23 plus 10/24, 6/23 plus 6/24 times 10/23, 8/24 times 6/23, and lastly 6/24. Okay, hit equals, and you should get 47/69. It's a lot of work for 2 marks. Hell of a lot of work. But it's what it is. Okay. So probability tree. So sometimes when you have like multi-layered things, you want to use a probability tree. So the probability a tennis player gets a first serve in court is 65%. So you can call it whatever you really like. So I'm going to say first serve. And I'm just going to call it in and out, just because I know that in tennis it's like inside the box or outside the box for it to be counted. But you could just say gets and doesn't get, or whatever you want. It doesn't make a difference. Probability that she gets this is 65%. And remember that they need to add up to 100 or 1. So actually, instead of a percentage, I'm going to write it as a decimal, because we don't really calculate with percentages anymore. So then that must be 0.35, because again, across branches, they should add up to 1. And if she gets her first serve in the court, don't know why I said it so weird, so another one, then it's win and lose. Probability that she wins is going to be 0.81, which means that would be 0.19. So as we're getting a second serve in the court. Okay, second serve in the court. So if it's out on the first one, chance that she gets it in versus out on the second one. Chance of getting it will be 84%, so that's 0.84, which means this would be 0.16. And if she gets the second serve in the court, then the probability of winning is 0.5959%. So that'd be 0.41. And okay, so she loses the point if she doesn't get it in. So instead of out, I'm actually going to change this to lose, because that's what it says. So it get a little bit complicated, tiny little bit in this question, but not too bad. Again, in terms of the marks, you lose a mark for every part that's incorrect, so any numbers or wrong branches and stuff. And then part B, it says find the probability of the tennis player winning the point. So there are two options, right? She either succeeds with the first serve and then wins, so that'd be 0.65 times 0.81. But there's also another option, right? She can miss the first serve, then get it in, then win, which would be 0.35 because she misses the first serve, times 0.84 getting it in the second time, and therefore 0.59 for winning once she's got it in on the second serve. So I want to put the brackets as well, 0.65 multiplied by 0.81 plus 0.35 multiplied by 0.84 multiplied by 0.59. 0.699996. So I'm going to write it out exactly because otherwise it's going to look a bit odd. Like that. Okay, so hopefully that makes sense. Okay, and for the last question today, we're going to be doing this. So there's three machines, and if it's produced by A, that's faulty. Okay, cool, and we need to draw a tree diagram. So what we need is, the first thing is whether or not which machine it goes to, right? So I can go to machine A, I can go to machine B, or it can go to machine C, and then for all of them it should be faulty and not faulty. So let's do that. So I'm going to put faulty and either NF for not faulty, or you can use F prime if you want to use the fancy probability notation. Okay, so what's the chance it gets produced by A? 40%. 35 for B and 25 for C. If it's produced by A, it has a 3% chance of it being faulty. So that'd be 0.97. 2% for B. So that's 0.98. And 1% for C. Okay. That's it for part A. So for part B, the component is selected at random. Find the probability it's from machine A and faulty. So this would be 0.4 times 0.03, which is going to be a very, very small number. Sorry, 0.03. So 0.4 multiplied by 0.03. 3 over 250. I'm going to leave it as a fraction. Actually, 0.12 works. Part C, that it's faulty. Great. So there are three ways, right? It's A and faulty, B and faulty, C and faulty. However, we've already worked out A and faulty as 0.012, so that gives us one fewer things to work out. But then we want B and faulty, which is 0.35 times 0.02 plus 0.25 times 0.01. So that should just be 0.07, right, and then 0.025, add that together. Okay, let me add that together. Or I'll just do the whole thing, it's fine. (43/2000), 0.0215, okay. Okay. So I think that's where we'll stop it for today. So again, this is just right before we're going to do the binomial distribution and hypothesis testing. We just need to make sure that we're okay with kind of probability in general.